Hey everyone, we are looking at the fundamental theorem of calculus. And with a name like fundamental theorem of calculus, you know it's going to be important, right? I like to say we put the fun in fundamental, but I suspect most of the time I'm putting the mental in fundamental. And occasionally the duh in fundamental. Anyway, what the fundamental theorem does, is that it gives us a 100% accurate answer to a definite integral. No more of these estimates from counting boxes or looking at trapezoids or Riemann sums, even if we have a lot of rectangles in our Riemann sum using our new fancy program. So here's what the fundamental theorem states. If g of x equals the integral of f of x dx, then the integral from a to b is equal to g of b minus g of a. And you might just look at that and go, huh? Basically, integrate, because if you integrate f of x, you get g of x, and then plug in your b, plug in your a, and subtract the 2. So let's take a look at this in action. So if we're looking at the integral from 1 to 4 of the square root of x dx, we're saying, what's this region right here? And I know we could use our new fancy program. In fact, let's use our new fancy program, program Riemann. I've already put my equation into my y1. So if I put 1 in, I put 4 in, because that's my lower and upper bound. Let's say I put 50 in. I'm going to go with kind of a lot of rectangles just to get a good answer. And percent, I'll do a midpoint Riemann sum. So it thinks about it. So 4.6667. So remember that number. See if we see it again. Hopefully we do. I suspect you even have a guess at what knowing this is a little off, you might even have a guess at what the exact answer is. Okay, so first of all, if we're going to integrate this thing, it would probably be helpful if we didn't have it written as root x. I'm going to rewrite this as x to the 1/2 dx from 1 to 4. So I integrate it. Remember, we add 1 to our exponent, so we have 3/2, and divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. I'm going to do that, plus our c. And then this is a bit of notation, what people do. Once you integrate and it's a definite integral, throw a vertical bar at the end, and then put the 1 and the 4 just after that vertical bar, like what you see there. It's just kind of a reminder, this is what I'm doing. So now we're going to plug in that 4, so we have 2/3 times 4 to the 3/2 plus c. I'm going to throw this in parentheses. Minus, I'm going to do the 1 in there, so I have 2/3 times 1 to the 3/2 plus the c. So notice what we have here. One, I have some fractions and root and exponents to deal with, but also I have a c that I don't know what it is. But then I have minus the same c. C minus c, that's gone. And in fact, on definite integrals, people don't even bother to write the plus c, which in some ways causes problems in that when you're doing indefinite integrals and you do need the plus c, you forget it way more easily. So it's so easily forgotten already, let's make it worse. Great. Okay, 4 to the 3/2, take the square root first, it's easier. So we get 2 cubed is 8, and then times 2/3, so 16/3. And then 1 to whatever, who cares? It's 1 times 2/3, so we have 16/3 minus 2/3, which is 14/3. And wait, 14/3 is 4 2/3. What did we have before? 4.6667. Huh, good. The system works. So when you're doing these things, you can check your answers on your calculator using that Riemann sum program that you've entered in. It will be really handy. Okay, let's look at another example. So we have the integral from, we'll do -1 to 2 of 3x squared minus 4x plus 2 dx. So in dealing with this, you just treat it, like how when if we were deriving something like this, you would just derive each piece and put the plus or minus in between. Same idea, no big deal. Okay, so integrating this guy, we have x cubed And then that 3 gets divided by the new exponent of 3, so 3 divided by 3 is 1. And remember, anytime you're integrating and you're doubting yourself, and this goes always, take the derivative. Even if you don't write it, just go, okay, derivative of x cubed, it's 3x squared. Yes, I got it. Okay, and then my x is becoming x squared, dividing by the new exponent. So I have minus 4 divided by 2, or minus 2x squared. Or if you derive it, yes, you do get 4x plus 2x. I'm not going to bother with my plus c because it's just going to subtract out anyway. I will throw my vertical bar and the -1 and the 2 at the end. Now I just simply plug in my 2, so I have 2 cubed minus 2 times 2 squared plus 2 times 2. There are too many 2's in this problem. You're welcome. Okay, minus, I'm throwing a parenthesis down, and then -1 cubed minus 2 times -1 squared plus 2 times -1. Okay, here's the weird thing. So say we end up managing to take an in-person test someday, and you have a non-calculator part. Obviously, when we're online, I can't stop you from using your calculator. But if we were in person and this is a non-calculator question, which it would be, this is actually a perfectly good answer. And the College Board people think the same. Because really, the College Board and I actually care more about can you do calculus more than can you do the arithmetic. So yeah, we can keep going though. I did the math earlier. This gives us a 4, and then we have a minus, and then this second wad of stuff gives us a -5. So this is kind of crazy, but like if we were to graph this parabola and look at the area from -1 to 2, the area with, even though it's this curved thing, the area is exactly, with 100% accuracy, 9. I love that. I love how like you get these weird shapes and you get these really tidy answers sometimes. It's just so cool. Of course, sometimes you don't get tidy answers at all. Okay, let's do one more example just for funsies. So we have the integral from, I'm going to mix it up, -pi/2 to 2pi/3 of sine x dx. And remember, I could check this by throwing that in my y1 and then using my Riemann sum program. I'm not going to do that for the sake of time. Okay, so what we're looking at here, I'm going to go ahead and draw a graph because I'm feeling wild and crazy. So remember that sine x looks like that. That's going 0 to 2 pi, and then, so -pi/2 is to here. And then 2pi/3 is about there. So we're looking at this combined region. So if I went from -pi/2 to +pi/2, that's symmetric and below the axis and above the axis. So if that was a pi/2 for the upper bound, it would actually go to 0 for the definite integral. Or if I had, say, 0 to 2 pi, that would also be a 0 because you have a blob on the top and a blob on the bottom of equal size, even though I didn't draw them that way. And this would be a negative value underneath, because if you think about this as a Riemann sum, if you drew that sample rectangle into that lower region, your y value is negative, and then your dx is positive because you're going from left to right, because -pi/2 to pi/3, 2pi/3. So that region being negative, if we were going that far. Okay, so if we integrate this guy, the thing that has a derivative of sine x is negative cosine x. Because remember the derivative of cosine being negative sine, so watching our signs there. Throw that vertical bar down and -pi/2 to 2pi/3. And then plugging in, so we have negative cosine of 2pi/3 minus negative cosine of -pi/2. Now, technically this could be a non-calculator problem too, and you could, use your unit circle and find that. For the sake of time, I'm not going to do that. This is so trippy, but if you actually did all the math and looked at the unit circle, you end up with, I love this, 0.5. The area, this region is exactly 0.5. In fact, if you looked at 0 to pi, just that first lump of the sine graph, the area of that guy is exactly 2. I love that so much. It's my favorite integral. I'm such a nerd for having a favorite integral, but I don't care. So there we go. So that's the fundamental theorem. Basically what it comes down to is this: integrate, plug, subtract. And then check your answers. Use your Riemann sum program on your calculator.